Okay, welcome, and we're going to be talking about chapter 10 here. Again, it's going to be a recorded lecture to keep us on pace, uh, and we will hopefully probably get through maybe all of this chapter here in this one recording. And again, that should keep us on pace here to make sure we cover all the chapters that we need to. Again, with the holiday and your exam this week, this way you can at least stay up with the material. So today we're going to be talking about chapter 10, and chapter 10 is nuclear chemistry, basically, and nuclear radiation. And we're going to talk about a little bit about nuclear chemistry. Some of the stuff in here will be a little bit of a review. Some stuff will be new, and we'll kind of tie some of the older stuff that we talked about at the very, very beginning of the chapter with what's going on in this chapter. So first thing we're really going to talk about is nuclear radiation. And let's talk a little bit about radiation. When we talk about something being radioactive, radioactive means that we have an unstable nucleus. And this unstable nucleus will sort of spontaneously emit emission to try to become more stable. And a couple of things that are important to remember is our atom, right? And our atom is really made up of those three subatomic particles that we talked about. We have our protons, right, which are positively charged. We have our electrons, which are negatively charged, and we have our neutrons, which have no charge, right? And a reminder that it is inside the nucleus where we find our protons and our neutrons, and our electrons, right, are out from the nucleus, again, traveling about in a pretty random pattern. A reminder that, again, the atom is mostly empty space. It is filled with those electrons, which are the smallest in terms of mass of the three different particles, the electrons being the least massive, while the neutrons and protons are very similar in mass, but the neutrons are just slightly heavier than a proton. So most of the mass of the atom is made up of that nucleus, and that's because, again, inside that nucleus here, inside that nucleus is where we do find both those protons and neutrons. And again, a proton and a neutron, each individually, are somewhere around 1,800 times heavier than any electron that we may come across. So really, we're going to talk a lot about these protons, electrons, and neutrons, and not necessarily the electrons here, but really more the protons and neutrons. And in a sort of nuclear reaction, we definitely deal with the changes that occur in that nucleus, basically, those protons and those neutrons. So radiation can be several different types of radioactive sort of particles that can exist. There are alpha particles, and alpha particles, as we'll see here, are positively charged particles. They have the alpha symbol, or as we will see sometimes, instead of the alpha symbol, they will also use the helium symbol there as another way to represent an alpha particle. We have beta particles, which are negatively charged particles, and they are also sometimes represented by E, or an electron, basically, and they have a negative charge. While we also have gamma rays, and gamma rays are kind of like neutral, no charge. They're really just pure energy. They're super high in terms of energy. And, you could almost equate each of these to sort of the subatomic particles that we find in an atom. So like our alpha particles are positively charged guys, our beta particles are negatively charged electrons, and our neutrons, sort of pure energy, no charge. So when we talk about an isotope emits radiation, and that's sometimes referred to as a radioisotope. And if you remember, we talked about sort of isotopes when we talked about protons, electrons, and neutrons. Isotopes are essentially the same element, but they have different masses, which means that they have basically a different mass number. And because they have a different mass number, they essentially have the same number of protons, but a different number of neutrons. And when we talked about sort of protons, electrons, and neutrons, remember that out of all of those sort of three subatomic particles, it is the protons that are what determines the element. So the number of protons determines the element you're talking about. And as long as we keep the number of protons the same, we are talking about the same element. So we can change the number of neutrons and get us an isotope. And that isotope will be the same element because, again, they do have the same number of protons. So a couple of things that we did talk about as well, and we'll see here, I think, in just a second, but one way that we could write these isotopes, sort of symbols, is we sometimes will put a number on the top left, and that is what is referred to as the mass number. And on the bottom left is where we put our atomic number. And remember that the atomic number is the number that you find on the periodic table. So when you look at a element, you see a couple numbers typically on there. And again, it is typically that number that comes above the symbol on the periodic table is your atomic number. And here we do have some different isotopes of magnesium here. You can see they all share the same atomic number, which is why it is magnesium. They all have 12. But the top number here is different, which is the mass number. And the mass number is, as we will see, the number of protons and neutrons that we find in a particle or an atom. So the mass number is the number of protons plus the number of neutrons, while again, the atomic number is the number of protons. A reminder as well, as we talked about way back in that chapter, this number down here, again, is the atomic mass and not the mass number. So a couple of reminders that when you do calculate something like number of protons, electrons, or neutrons, the atomic number or the mass number, those are all whole positive numbers. So again, a reminder that that number on the bottom of the periodic table there underneath the symbol is not the mass number. So only really the atomic number you could find up there on the periodic table. Again, here are some isotopes of iodine. Again, they all have 53, which is the atomic number. They all have a different mass number, which basically means they have a different number of neutrons. And again, that makes some isotopes of each other. So again, an isotope is the same element with a different number of neutrons, which means it has a different mass number. And again, depending on the mass number or that isotope, as you can see in this table as well, some are radioactive, some are stable. Same thing over here. We have some radioactive guys. Uranium at the end here, pretty much radioactive all the way through. Now, let's talk a little bit about, again, these symbols that we sometimes see and some common symbols that we see in nuclear chemistry. So again, the alpha particle is basically 2 protons and 2 neutrons. And that basically is how we get to our mass number of 4, right? 2 protons plus 2 neutrons, which is the definition of mass number. Protons plus neutrons gives you 4 for the mass number. Again, the atomic number, which you could find from the periodic table, is 2 for helium. And again, as I mentioned before, alpha particles sometimes display like that. Sometimes the alpha particle will actually have the 4 and the 2, the 4 being the mass number, the 2 being the atomic number, are again very common in nuclear chemistry. People will just use helium as well. Again, the 4 being the mass number, the 2 being the atomic number. The beta particle here, again, is basically a high-speed electron, can be used with the symbol, the beta symbol, or again, the beta symbol with a 0 on top for the mass number, a -1 for the atomic number, or as you see here as well, very commonly, kind of the E is used to sort of represent an electron, and again, with the mass number. Now, a positron is a positive electron, and it basically has the same symbols as a beta particle, except that it is positive, basically. So it will also use the beta symbol, but it will most commonly have something like a plus on it to indicate that it is the positron and not the beta particle. So again, there usually will be some type of plus to distinguish it from the one above. You'll also use the same symbol, but again here, this is going to be a +1 instead of a -1. And again, they'll also use the same E symbol sometimes, but again, the +1 will definitely be indicated as well on there. So you can distinguish it between a beta particle. Again, if you just see, sort of the beta symbol, or and 9 times out of 10, if you just see an E sort of written, probably a safe assumption they're talking about a beta particle. Again, very common if they are talking about the positron, something with that plus is usually always included. Now, the last one is a gamma ray, and that's again just pure energy, and that basically will have the gamma symbol, and it's basically 0 and 0 in terms of the mass number and the atomic number. So those are some common particles that we come across when we're doing nuclear chemistry. And this table as well displays a couple of other sort of symbols that we also very commonly come across. So the first several here we just talked about, but also a proton is sometimes used a lot in these sort of equations. And a proton is represented with a hydrogen and a 1 for the mass number on top, a 1 for the atomic number on the bottom. RAP is used to represent the proton, also with a 1 and 1, 1 for the mass number and 1 for the atomic number on the bottom. And also very commonly in these guys, a neutron is included a lot of times in sort of these equations. A 1 is 0 and an N is used there as the symbol. Or again, sometimes just the N is used as well. Now, we're going to talk about sort of balancing nuclear equations and so forth in this chapter. So, this sort of table here in the last couple of slides, it's really important to know the symbols, and also really important to know, obviously, besides the symbols, the mass numbers that go with those symbols and the atomic number. Because a lot of times they may just say, hey, you did an alpha particle, and you're supposed to know, oh, an alpha particle is helium-4 or if you want to use the alpha symbol, something like that. But important for balancing, as we'll talk about, is obviously knowing those numbers as well. So important to know, again, the symbols and also the numbers for the mass number and the atomic number. So when we talk about radiation, basically radiation is given off in the form of waves. So it's emitted as some type of radioactive sort of element starts to decay. It will give off a lot of this energy in the form of these waves. And depending on the type of emitter it is, as to perhaps what type of protection you may need to use, radiation protection can require paper and sort of clothing for alpha particles. Not too bad. A lab coat and some gloves for beta particles. If you're using something that's a gamma emitter, sometimes thick concrete walls, a lead shield is needed for that. So in terms of sort of penetration, say in the tissue, alpha particles only go so far. Beta particles go a little bit further, and things that are gamma rays, they penetrate very, very far into the skin. And that's why the level of sort of protection that you need does sort of change depending on the type of emitter it is. So when we talk about something being emitted, it is some type of particle being given off as a result, usually in this case, of a nucleus sort of going through that radioactive decay. Obviously, you could protect yourself. Obviously, like most things, limiting your exposure is really important. That helps protect you. Obviously, you don't want to be standing near something that's radioactive for a long, long, long period of time. And obviously, increasing your distance from something that's obviously radioactive, giving off sort of particles, can definitely help you sort of protect yourself as well. So here's just some of the examples you can see in the picture. They got some shield going on. They got some lead, and he's got obviously gloves, coat, also a lead vest on, and so forth. So he's probably working something in probably the gamma ray sort of area there. And again, as you can see here, the alpha, beta, gamma will go travel further in sort of air. You can see alpha will only go 2 to 4 centimeters, so maybe not as much protection is needed as, again, as something like a gamma ray to go 500 meters. And you can see also the gamma ray can travel very, very far into sort of your tissue as well. So always important, if you happen to find yourself working with some type of radioactive material, maybe you're doing some type of research or in your laboratory or something like that in your future, it's always, always really important to A, know what you're dealing with, and B, know what type of emitter it is. So you know you could obviously provide yourself with the proper protection. So let's talk about sort of nuclear equations and how to balance nuclear equations. And nuclear equations or nuclear reactions are different than chemical equations or chemical reactions. So chemical reactions, if you remember when we balance equations, there is a conservation of the elements. And what that means, if you remember, if you were to balance equation, you started with 4 carbons on the left-hand side, you need to end up with 4 carbons on the right-hand side, right? If you had 6 oxygens over here, if you balanced it in something, 6 oxygens needs to end up on the right-hand side. Again, it may be in different compounds, maybe in different formulas, but you do have that sort of conservation of those elements. Now, when we have a nuclear reaction, it's actually different. In a nuclear reaction, we actually don't have the conservation of those elements. We actually start with one element, and we oftentimes will form 1 or 2 new elements. And that's a tremendous difference in sort of a chemical reaction versus a nuclear reaction. And remember that the thing that determines whether or not we keep the same element is the number of protons. And that means in a nuclear reaction, we're actually changing the number of protons that we start with, and we're getting some new protons on this side, and we're making some new elements. And obviously the protons are and neutrons are in the nucleus. That takes a tremendous amount of energy to do that. And that means that a typical nuclear reaction will produce a lot more energy than any of your sort of exothermic chemical reaction would do. So you get a tremendously more energy being sort of produced in these reactions. And again, that is because we're playing with really the particles in the nucleus. In a chemical reaction, what we're playing with is essentially electrons. Electrons are on the outside of the atom, so when they come together, they interact very well, and we're not really dealing with anything in the nucleus of the atom, but here we are dealing with the nucleus of the atom. We're going to change protons into neutrons, neutrons into protons, so very, very different in terms of the type of reaction that occurs. Now, when we balance nuclear equations, or we have nuclear equations, we do want to balance them, and it's a little bit different than how we do chemical equations. So let's talk a little bit about sort of things that we will see in an equation and a couple of terminologies that we sort of hear. And one is an emitter. So if something is being emitted or decays through some type of emission, basically that particle will be found on the product side. So an alpha emitter means that when you would write an equation, you would basically have an alpha particle on the product side. It's like it's being given off. Now, when we balance a nuclear equation, there's basically 2 things that you have to make sure of. You have to make sure that when a nuclear equation is balanced, that all the mass numbers on the left-hand side of the arrow equal all the mass numbers on the right-hand side of the arrow, while all the atomic numbers, when you add them up on the left-hand side of the arrow, equals all the atomic numbers on the right-hand side of the arrow. So balancing, not too bad. Just going to make sure everything adds up together. But things do change, and this is why it's important to know these particles and also know, the atomic number and mass number. So if something is emitted, it's going to be on a reactant side, as opposed to, as we'll see a little bit later on, if something is bombarded or some type of capture, that's going to be on the reactant side in terms of those particles. So basically, as you can see here in this balanced equation, we want to make sure that when we add up all the mass numbers on the left, so on the left-hand side, we have a grand total of 251. They equal all the mass numbers on the right-hand side. So that's 247 plus 4. So 247 plus 4 gives you also 251. Now you can see that's in multiple things, but it does add up to the same number. We also want to make sure that our atomic number is balanced. So we got 98 on the left. We have 96 plus 2 on the right. Again, 96 plus 2 equals 98. And we're balanced in both of these sort of ways. So again, this would represent the balanced nuclear equation. It has the balanced mass number on the left and right, and balanced atomic numbers on the left and right. This is also an alpha emission. The alpha particle here is on the product side. So again, that emission means that we will find this little particle here on our product side. So when you go to write the equation, you want to write the equation, usually there'll be something missing. So this is where when we go to balanced equations, especially nuclear equations, your friend is the periodic table. And because on the periodic table, as we talked about, when you super zoom a box, the one thing that you could find on the periodic table, again, is the atomic number, which again is the number of protons that there are. And it also tells you the element that's involved. So in a nuclear equation, sometimes something's missing, or you got to find like a missing element. And the easiest place to start with is the atomic number. Because once you find the atomic number that's missing, you can find the element and obviously the symbol that goes with it. And once you find the element and the symbol, what's left is then you can find basically the missing mass number. So let's take a look at this guy here and see how we get to that sort of answer on the bottom. So basically the first thing that we're given is we're given our starting guy here, 86. And we have not sure plus basically our alpha particle. Again, alpha particle here. This is an alpha emission. So what do you want to start with? Really, the atomic number is really a great place to start. So what we look at here on the left-hand side is, on the left-hand side of the arrow, 86 for the atomic number. We're not sure here, but we do have 2 over here. That tells us right off the bat that our missing atomic number is 84. And this is where the periodic table is really helpful. You would go to the periodic table, and number 84 on the periodic table is PO. And we already know that its atomic number would be 84. Now, we also need to figure out the mass number that's missing. So on the left-hand side, we have 222. On the right-hand side, we're not sure the mass number there, but we do have 4. So if we subtract 222 minus 4, that gives us a missing mass number of 218. And that's how we get down to our missing symbol here. And this on the bottom would represent the balanced nuclear equation. Again, if we add up the atomic number, 86 on the left, 84 and 2 is 86, so that balances. On the left on top, 222 in terms of mass number. We have 218 here and 4 here. And again, when you add those together, you're looking at 222 on top. So that would represent our missing mass number, our total mass number, and again, our balanced equation here. So always good to start with periodic table and the missing atomic number. Now, mind you, sometimes the missing thing may be a particle. And most of the cases, you'll be able to figure it out from the periodic table, but it could be like a neutron or something like that, or a proton, but usually you'll be able to figure it out probably by using the periodic table. Now, a beta particle, again, is that electron, and something that it goes through a beta emission again. Again, the key here is emission, so that means on our product side, we will have that beta particle coming off. And the important part here as well is the beta particle is -1 here, which actually does affect sort of the math when you go to balance it. So let's take a look. So here, this is a beta emission. So again, we have a beta emission because we see our beta particle over here on the product side. And again, you can see you can use that E symbol instead of the beta symbol. And when we look at this, we want to kind of approach it the same way. So we're going to take our 4219K. Again, we're not sure what we're missing, but we do have some numbers here. So on the left-hand side, our atomic number is 19. On the right-hand side, we actually have -1 for the atomic number, which means in order to get me to 19, our missing atomic number actually has to be 20. 20 and -1 gives you 19 on the right and 19 on the left. And 20 here would be calcium on the periodic table. So if we go to periodic table and look up number 20, we see it's calcium. Now for our mass number, we have 42 on the left, 0 on the right, which means our missing mass number is actually going to be 42 in this case. And again, if we add up everything on the left on the bottom, atomic number 19, 20 and -1 gives us 19, so we're balanced. 42 on the top for our mass number, 42 and 0 gives us 42. So again, over here would represent the balanced nuclear reaction. Again, you can see there is no conservation of elements in this case. We have basically new elements being formed, but again, it's balanced as we are looking for basically same mass number on the left and right, total number, not individually, but total when you add it all together. And same atomic number on the left and right when you add them together. Now, again, a couple of other sort of common reactions that we sometimes will see here. A positron is a proton that is converted into a neutron and a positron. So you may be asked, how do you get that positive electron? And it's actually when we take one proton and we convert it into these two particles here, we make a neutron, and as a result, a positron is made. So remember, that's like our positive electron. And when we have a positron emission, we actually need to subtract. So again, 25 here, if we had just this on the right-hand side, 25 -1 will give you 24 is the missing mass number, atomic number. And our mass number would be 49 plus 0 is 49, and we're balanced on each side. Gamma, you can see here, nothing changes, as really this is 0 and 0. It's basically will not change. The mass will change a little bit, but it was basically 0 and 0. Now, another sort of one that you'll see. So again, when we talk about emission by some type of particle, that again means that particle ends up on the product side. A very common one where we see a particle on the reactant side is something known as electron capture, and that would be a symbol plus an electron on the reactant side. So that's a common sort of nuclear reaction that you see in electron capture. And sometimes you'll see the word, or somebody will say bombarded. So like this element was bombarded by neutrons. So if something's bombarded, that means you're pretty much adding it as well. So we'll just say we bombarded with a neutron. So bombarding something means that that particle will end up on the reactant side. So there are a couple cases where things will end up sort of on the reactant side in terms of the particles, and those are the two common ones: electron capture, or you bombard something with either a neutron, an alpha particle, something like that. But anything about emission, it's emitted, it decays through this process. Those are all going to be really emissions, and those particles will end up on the product side. So let's take a look here. If we have this guy, again, what we want to start with is our atomic number. So 95 here on the left. We have 2 on the right. That means in order to get us to 95, 95 minus 2 is 93. Again, your periodic table is going to be helpful here. So you would go to the periodic table. You would see number 93 is NP. That is our atomic number, which would go on the bottom. Now for our mass number here, we got 241 on the left. We have 4 on the right. So to figure out what we're missing here, I won't put 0 there. We'll go question mark. We basically just want to take 241 minus 4, and that gets you something like 237 for our top number there. And that would be our missing one. So again, if we write a complete balanced equation, it would look something like this. And again, this also would be a alpha emission, as that particle is on the product side. So here's a few examples. So if you like, you could pause the video if you like and take a second or two to try it, and then we'll talk about it here. Okay, so hopefully you pause the video, you gave this a shot here on yourself. If not, pause it now and come back. So let's take a look at this. Uranium-238. So another thing that we talked about is sometimes isotopes are written like this. And what that number represents is the mass number. So we would start with our uranium, which is 238. Not given to us is the atomic number, but again, this is where our periodic tables can come really in handy. So 92 is the atomic number for uranium. Alpha emission means that emission is going to be on the product side, and that's going to be our alpha particle, which again, you can use the helium symbol. If you want to use the alpha symbol, you could do that as well. And we want to balance it. So we have 92 on the left for the atomic number. We have 2 on the right. So to get us to 92, our missing atomic number would be 90. Basically 92 minus 90. 92 minus 2 gets you 90. And that means if we go to the periodic table and look at number 90, it is TH. Now we want to do the same thing for the top here. So 238 on the left for the mass number, 4 on the right. So that leaves us 234 there for our mass number on the right-hand side. Again, balanced, same atomic number on left and right, same mass number on left and right as well. Again, neon 24 means it is 24 for the mass number. If we go to the periodic table, we see neon's number 10. And again, emission and its beta, so that is going to be on our product side. Now, when we're adding up our atomic number, we got 10 on the left. And again, the negative's important here, so that is -1. So we actually need 1 more here in terms of the atomic number, 11. And that would get us sodium. 11 and -1 is 10, and 10. 24 for our mass number up on top. Continuing on, nitrogen 13. Again, getting our atomic number there from the periodic table, which is 7. This is a positron emission, which looks just like a beta particle, except that it is +1 here. So in this case, to balance it out, we have 7 atomic number on the left, 1 on the right. That means our missing atomic number is 6, and that's going to be carbon. And our missing mass number will be 13. 13 and 0 is 13, and 13 on the left-hand side. And lastly, we have an electron capture. So this is going to be beryllium with a 7. Going to the periodic table, we see 4. Now, this is one where we have an electron capture where actually the electron will be on the reactant side. And that means we just add up the bottom. So 4 minus 1 is 3 as our missing atomic number. And number 3 is lithium. And 7 and 0 is 7 for our mass number there on top. So again, all these would represent the balanced nuclear equations. And again, it's basically same mass number total on the left and right-hand side of the arrow, same atomic number total on the left-hand side and right-hand side of the arrow. And again, that missing atomic number and the periodic table is what you could use basically to figure out, what's missing. Here's just a little sort of thing that shows you the sort of changes that occur. So an alpha particle mass number changes 4, atomic number changes by 2. A beta emitter, atomic number changes by 1. Positron, we go down by 1 in terms of the atomic number. And a gamma, everything's the same in terms of where it started and mass number, atomic number. So again, here's the symbols and how things change depending on what type of emission particle it is. Now, there is a way to sort of produce radioactive isotopes, and one way that we can produce radioactive isotopes from a stable isotope or a stable nucleus is by converting it into an unstable nucleus. And by doing this, we bombard it, and that's that other keyword I was talking about earlier. So when you bombard something, that's basically like shooting a particle at it. And in this case, as you can see here, we're shooting basically an alpha particle over here at this boron. This boron's like unstable now after you hit it with that, and it basically will then produce a new nucleus that occurs. This process where you sort of shoot a radioactive particle at a stable nucleus to produce a new radioactive nucleus, this is the process which is referred to as transmutation. So transmutation is where you sort of kick off this radioactive decay process, if you will. You sort of do it, a lot of times use an alpha particle, sometimes you can use a neutron. And again, it basically just takes something that's stable and it's like, whoa, I'm now unstable. I got some different particles happening here. And it will sort of go through a process where it will kind of split into some new nucleuses that are formed. And a lot of times in these processes as well, it will also produce some particles like neutrons. So let's take a look at one here. So if we wanted to produce a new radioactive element by shooting basically a neutron. So we would be bombarding this guy with a neutron. And we can see we get an alpha particle off. But we can still do it basically the same way as we did before. So if we look at the atomic number, that is 27 on the left. We already have 2 on the right, which means our missing atomic number is number 25. If we go to the periodic table, number 25 is Mn. And we would do the same thing for our mass number. Up on top, we have 59 plus 1 gives you 60. On the right-hand side, we have 4. So to get it to 60, we would need something like 56. And this would be our new radioactive sort of nucleus that is produced as a result of that. So again, this is what is referred to as a transmutation. We're basically bombarding the stable nucleus with a particle, which is a neutron in this case. It's going to create an unstable nucleus here, and we're going to get something like this guy in this case. But in terms of actually figuring out, you can see hopefully it's the same sort of process as what we did before. Now, how do we measure sort of radioactivity? One way we can measure radioactivity is through the use of a Geiger counter. It detects beta and gamma radiation. And it basically uses ions to produce some type of electrical current, a voltage, and it kind of makes a noise like beep, 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 beep. And obviously, the louder the noise, the more radioactivity you have. Usually has a wand, as you can kind of see here. And you kind of go around and it basically will beep. The louder the beep, the more radioactivity it is. Usually you use it, obviously, if you're using some type of radioactive source, you sometimes will use it after you clean up as well to make sure you didn't contaminate anything as well. You know, if you hold it up in the air, it will make some noise. There is background radiation around us. Hopefully it won't make tremendously loud noise, but it would probably still make a little bit of noise. And there's some units of radiation that we sometimes will use. And one unit of radiation is a Curie. And that measures the activity as the number of atoms that decay per second. A rad is a radiation absorbed dose, and that measures basically the radiation that's absorbed by tissue in the body. And a rem is basically the radiation equivalent. And what that measures is basically sort of the biological damage that's caused by sort of exposure to radiation. And depending on the type of radiation, alpha particle, beta particle, gamma particle, your REM factor will go up. And obviously gamma would be more, as we talked about earlier. It penetrates further into the skin, obviously, and so forth. So a little bit more damaging, obviously, than maybe alpha particles. But it has something to do with sort of time and, you know, how long you've sort of been there. So that's what REM is basically the rad, and the factor has to do with the type of radioactive particles that you're basically being exposed to. Now, just to give you sort of an average sort of idea, again, like I said, if you held up sort of that Geiger counter in the air, you would hear a little bit of beeping, and sometimes referred to as background radiation. And here are some sources of some average radiation that a person sort of receives. You can see from the ground, air, cosmic waves, we get some stuff. Obviously, X-rays and traveling in the air, planes, television, cigarette smoke, and so forth. So, you know, we are exposed to sort of radiation all around us. And again, the idea is hopefully not a lot for a very long period of time. But, you know, there is some what's sort of considered background radiation. Now, when an isotope sort of starts to go through the decay process, there's a part of it which is known as the half-life. And the half-life, basically kind of like what the name implies, is the amount of the isotope left over after its half-life. And basically the amount of the isotope that's left over after every half-life is half of what you started with, basically. So let's just say you started with 10. After the first half-life, you would divide it by 2, and you'd be left with 5. After, say, a second half-life, you would divide it by 2, you'd be left with 2.5. And if we went through another one, you divide it by 2, you'd be left with, you know, something that's half of 2.5, which is, I think, 1.75, if I'm not mistaken there. 1.25 would be a better number there, and so forth. So every time you go through a half-life, you lose half of what you started with. So, you know, somewhere around 10 half-lives, you know, pretty much all of it is sort of gone at that point. And that's what you see here. This iodine 131 started as 20 grams of it, went through a half-life, we're down to 10 grams. And you can see as it starts decaying, we start to produce other new nucleuses in that process. Goes through another half-life, we're down to 5, we're down to 2.5, and then obviously you can continue down that process. So you can see here in this chart, after one half-life, half of it's gone, next one, and like I said, probably about after 10 half-lives, as you can see, it's pretty much all gone by the time I'll get all the way down there. Now, half-lives could be as short as seconds, could be minutes, could be days, could be hours, could be years. So different radioactive isotopes have different time periods, if you will, for their half-lives. And again, like I said, could be as short as seconds or minutes, could be as long as many, many, many years before it even loses half of what it started with. So when we think about sort of radioactive isotopes and maybe some of the applications of them, these are some naturally occurring isotopes tend to have very long half-life. So you can see here carbon-14, 5,730 years before half of it goes away. This is like uranium-238. They use uranium, for example, in nuclear power plants and so forth. And this particular isotope of uranium has a half-life of 4.5 times 10 to the 9 years. None of us will see one half-life of that, or a part even of the half-life. That is a lot of years. So you can see some are super long, which again, as we'll talk a little bit about perhaps towards the end, nuclear power, if you will, and sort of the byproducts of it, because they use things like uranium and so forth. These things stay around for a very, very, very long time, and they stay pretty active for a very long time, which is, some of the maybe downfalls of that. How do you store it? Where do you keep it? Who watches over it for that many years? Well, obviously, if we're using something for medicine, for example, like down here, we may want something obviously with a very, very short half-life, right? Otherwise, your follow-up appointment would be a lot of years down the road, right? So anything that's used in sort of medicine, usually maybe minutes, hours, occasionally days maybe, but maybe nothing very, very long in terms of half-lives, because obviously they wouldn't want somebody walking around with something that's radioactive for a long period of time. That would not be good. So usually very short half-lives is used in medicine when we want to use it. And we can use radioactive isotopes for medicine, for example, to treat things, shrink tumors, for example. We could use it for scans and so forth. Because the nice thing about, say, a radioactive isotope, for example, is in the body, it will behave like the non-radioactive isotope. So, for example, if you want to know something about copper, for example, and how it's working and so forth, you could actually use a radioactive version of copper, and you can follow the radioactivity. And by following the radioactivity, you can see pretty much where it is, where it's going to go. And the nice thing is it will basically do the exact same chemistry as the non-radioactive version of copper, but you have sort of a way to trace it, for example. When we use sort of radioactive isotopes for scans, it goes into the body, it basically behaves just like that element in the body, and when we scan it, it obviously kind of highlights it, if you will, on the scan. So you're able to really see sort of different parts of the body in the scan that's sort of highlighted using these radioactive sort of elements. So if we have sort of a half-life question here, if iodine-123, the half-life is 13 hours, we want to know how much of a 64 milligram sample will be left after 26 hours. So really for us, sort of these simpler sort of half-life problems, what you really want to figure out is basically how many half-lives occurred. So we're going to want to go a total of 26 hours. Each half-life is 13 hours. So if we divide those two, that tells us this thing has gone through 2 half-lives. So basically, as we see here, we would want to start with our 64 milligrams divided by 2. That would be how much would be left over after the first half-life, which would be 32 milligrams. Then if we divide this by 2, this will tell us how much is left after the second half-life, which would be 16 milligrams. And that's what we see here on the bottom. So when you're approaching these type of problems, what you want to figure out basically is how many half-lives it went through. And basically the simple way of doing it is divide by 2 that many times. So take 64 divided by 2 once, and 64 divided by 2 twice gets us down to 16. So here, why don't you take a second again, if you want to pause the video here, and take a moment here and try to figure out the answer, and then we'll talk about it here in just a second. Okay, so hopefully you paused it. If not, again, you can pause it and work it out yourself to make sure. And we'll take a look at it here. So what we know is the half-life is 8 days in this case. And we want to know how much will remain after 32 days. So again, we could divide 32 by 8. That is 4 half-lives is going to go through. So we're starting with 100 milligrams. We're going to divide it by 2, which will give us 50 milligrams. That's after our first half-life. We'll divide it by 2, which will give us 25 milligrams. That's after our second half-life. Divided by 2. That'll give us, we got there, 12.5 milligrams after our third half-life. We'll divide it by 2 again. Going to give us 6.25 milligrams. That's after our fourth half-life. So here again, we figured out the total number of half-lives there was and divided by 2 that many times. Any questions on that? So that's not too bad to sort of figure out, how to calculate the half-life. Now, excuse me. So again, you could kind of work your way backwards as well. If you figure out, if you're told, for example, how much was left over after a certain number of half-lives, you could kind of work your way backwards. So as we talked a little bit earlier about sort of medical applications of radioactive isotopes, again, we typically want to choose those guys that have short half-lives. Again, you wouldn't want, obviously, anything that involves a really long half-life. Otherwise, it would be a very long time in terms of sort of your follow-up procedures and so forth. So here's sort of a thyroid scan over here, and you can see again by using sort of radioactive isotopes here. When you do a scan like that, again, it really just sort of highlights those areas for you. And here's just a table of some common use of some isotopes over the years. And again, you can see the most part here when we look at it, maybe the highest is days in terms of radioactive half-lives. Again, a lot of them are minutes, hours, and stuff like that. You can see here things from GI tract diagnosis, like a blood flow sort of tracer, tumor detection, abdominal imaging. We have some treatment of leukemia. Years ago, they used to implant radioactive sort of seeds into tumors to try to shrink them as well. They probably will do some of that as well still today, I think. Treatment of brain cancer here. Again, imaging of the skeleton, heart muscle, and I think that's what the picture was we saw on the previous page as well. So again, there's a lot of sort of applications of these guys. And again, the main idea here is that they will basically behave the exact same way as sort of the non-radioactive element in the body. So when you put it in, it will basically behave sort of like normal, but you get sometimes an added benefit of being able to sort of follow where it's at, being able to scan something, and obviously be able to treat some things because it will sort of enter your body and behave like the normal one, except that it does have some of these radioactivity sort of properties to it. So we're then going to talk about nuclear fission and fusion and the difference between them. So let's start with the fission reaction. In a nuclear fission reaction, a large nucleus is bombarded with a small particle. So this is what we were talking about earlier, bombarded again, a nucleus, perhaps a neutron. It becomes unstable and it splits off into two nucleuses, and usually will produce, a bunch of neutrons as well. And in addition, it will give off a lot of energy. So in a fission reaction, this is actually the reaction that is used, for example, in a nuclear power plant. Also, like a nuclear bomb, for example, is sort of a fission reaction. So as we talked about before, because these reactions involve new elements being formed, and we're changing the elements, we're changing the sort of composition of the nucleus, it gives off a tremendous amount of energy. And basically a nuclear power plant, for example, and a traditional power plant, they all sort of work the same way. And they all basically work by heating something like water. Water turns into steam. Steam goes out to like the turbines, out to the generators, and you get lights. The difference between sort of a traditional power plant and a nuclear power plant is how they heat the water. In a traditional power plant, they heat the water a lot of times with coal, so they burn coal and an exothermic reaction, and that heat from that reaction will heat the water and go through it. Now, in a nuclear power plant, they use a fission reaction that involves uranium, basically. And they basically do this deal with it. They shoot a neutron at uranium, and like I said, it splits off into two new nucleuses, just like we got on the right there, produces a whole bunch of neutrons and a ton of energy. And that ton of energy is used basically to heat the water. So power plants are basically work the same way. It's just sort of how they heat the water. Now, because a nuclear reaction gives off, about 600 times maybe, or even more than that amount of energy than, say, burning coal, is very efficient at heating that water. But both have some of their drawbacks. Obviously, a nuclear power plant, you're going to get all these nuclear waste products that, based on those half-lives and some of those ones that we saw before, will be around a very, very long time. So, what do you do with it? Who keeps it? How do you store it? Traditional power plants, when you burn coal, you get a lot of air pollutants and so forth. So, they all have sort of their downsides and their benefits as well. So why does a nuclear power plant not go crazy and sort of explode? And that's because they do a couple of things. They basically keep the amount of uranium under what is referred to as the critical mass. And what is the critical mass? Well, the critical mass is when you do this sort of reaction, this fission reaction, and you make these two new nucleuses and you make a bunch of these neutrons and a lot of energy. The problem with this is, as part of the product, you're making what really starts this reaction. So if you leave it uncontrolled, you could get what is sometimes referred to as a chain reaction. And what that is basically this guy goes through a fission reaction, he splits, these guys get hit with some new neutrons, they split. And before you know it, it grows sort of exponentially. You keep getting this reaction, continues to grow exponentially. Every time it splits and does this reaction and starts again, you produce a lot of energy, right? So if this was uncontrollable, it's going to be out of control, right? It's going to exponentially grow energy and energy, radioactive particles sort of everywhere. And to keep this reaction going and sort of self-sustain, you need what is known as a critical mass of, say, something like uranium. Right? And if you have a critical mass of uranium, it will keep this reaction going and going and going and going, basically. So in like a nuclear power plant, what they do is essentially will keep it under critical mass. And in addition, they have what are sometimes referred to as well as control rods. And these control rods are neutron absorbers. And that's really good because, as you can see, what basically keeps this reaction going is the neutrons. So they have these control rods which basically will take these neutrons out of these reactions. And by doing so, it keeps the reaction basically kind of under control so it doesn't go really, really sort of crazy. So here's a fission reaction, as you can see here. Again, uranium-235, which is sort of what happens again in a sort of power plant, nuclear power plant fission reaction. We're bombarding this guy. This uranium then becomes unstable, and then it splits off into two new nucleuses, and there's our neutrons. And again, in an uncontrolled situation, these neutrons are free to come back and start this whole reaction over and over again, which would be that chain reaction. Again, you could kind of keep it controlled by using something like control rods, which sort of eliminates hopefully that process. Now, these two products that are formed here are not always the two products that you get when you do this reaction. You can get different products, and it's sort of hard to predict which products that you'll get, but you'll get some new ones. But again, some of these byproducts of these reactions also have very, very long half-lives and are around for a very long time. And again, here's a much prettier picture of what's happening. Our neutrons hitting our uranium becomes unstable, splits off into our new ones. And again, lots of energy here. And you can see here, oftentimes we'll produce more neutrons, which, like I said, can keep this reaction perhaps going and going. But if we had sort of a fission reaction and we wanted to write the balance equation or figure out what's missing, we would follow the exact procedures we did before, but we just have a few more things in the equation. So we would follow here on the left, and that is 92 total for our atomic number. On the right-hand side, it is 52 total. That means that our missing atomic number is 92 minus 52. That looks like a 40. Again, we would go to the periodic table. And on the periodic table there, number 40 is ZR. So our missing guy here is ZR with an atomic number of 40. Now, when we do our mass number, we got 1 on top, and 235 is 236. We have 137 here. Now, the coefficient here is important. This was 2 times 0, which is 0. But when you times it by the guy on top, 2 times 1 is actually 2. So you do have to take that coefficient into account. That actually gives us a total of 139 on the right-hand side. So we would take 236 minus 139. Gives us 97 as our missing mass number in this case. So again, even though it has more stuff in it, you still want to approach it the same way as balancing the equation. Missing atomic number, periodic table to get to your symbol, and add up our mass numbers. But again, if you do find yourself with some coefficients, you do have to add them or multiply them across. So again, here, just to refresh that, we basically went 2 times 1, gave us 2 for the mass number. This was 2 times 0, which gave us 0 for the bottom. And again, the coefficient is important here for the balancing. I kind of jumped the gun, but here's a much prettier picture than what I drew, I think, in terms of the chain reaction. But again, these fission reactions can continue on sort of exponentially if you have the right amount of mass, which is that critical mass. And again, what starts this reaction, as you can see here, is a neutron. And again, neutrons are made in every step of the reaction, basically. And these neutrons can again continue to hit more uranium and continue this process. And as you can see, it's growing sort of exponentially. Again, every time energy being released until obviously an enormous amount of energy is being released in these sort of chain processes. All right, now to finish up here, fusion is different than fission. So fission is when we take a stable nucleus and we hit it with a small particle. In fusion, we actually take 2 small nucleuses and put them together to make a larger nucleus. And this occurs at extremely high temperatures, like you're vacationing there on the sun. Yeah, that type of temperatures. So fusion occurs at extremely high temperatures like what you find on the sun. And that's when we combo two small nucleuses into a larger nucleus. All right, so that is chapter 10. Not too bad, nuclear chemistry. And that should wrap it for chapter 10. That will then bring us to chapter 11, which I believe we're going to get into some organic chemistry here to finish out the semester. So I thank you for listening, and hopefully you should be watching this. And obviously, if you have any questions, always you can email me and ask me. But please watch this a couple of times if you need to, or if you do have questions. But please keep up with everything, and we're down to just a couple more chapters to go. All right, I'll see you next time on the next either recorded lecture. I think we might have one more before we come back to live. Have a good rest of your day, morning, or afternoon, depending on when you're watching this.